Alright, in this video we're going to go over the last two questions from the Chapter 7 practice test. And so we're given a differential equation, and we're asked which of the following is an expression for y of t. In other words, which of these is a solution. And if we're asked to actually solve, the only method that we know in our class to actually solve is separable differential equations. There are other methods that you will learn in later calculus classes, or if you take just differential equations. But for us, it has to be separable. So we'll go ahead and do that. There is sort of a shortcut for this problem, and we'll talk about that in a minute. But I just want to practice, we're reviewing here, how to actually separate and solve. So I need to take this and move the y to the other side so that I have y and dy on one side, t and dt on the other side. And k is a constant, so it can stay on either side. It doesn't make a difference. So if I do that, I'm going to get 1 over y dy is equal to k dt. And then we integrate both sides. And the integral of 1 over y is the natural log of the absolute value of y. And on the right-hand side, the antiderivative of k is just k times t. K times t, and then a plus c. And we only need a plus c on one side. Because we're talking about a population of yeast growing from some time, it's safe to assume that y will always be positive. Now, we could absolutely make the case that, well, if we have 120 grams at time t equals 0, we had to have some smaller amount of time or some smaller amount of yeast at time t equals -1. So it's not guaranteed that y has to be positive here, but it's safe to assume that we're only going to be dealing with, or actually, excuse me, I've been saying that, that's just not right. Y is the amount of yeast here. So we can certainly never have a negative amount of yeast. You either have some or you have none, but you can't have a negative amount. So that will always be positive, and thus we can ignore safely the absolute value bars here. And now when I solve this, I'll use e on both sides as the base to get rid of the natural log. So e to this power and e to this power. So on the left, that's just going to give me y, and on the right, it's e to this whole thing. And I know from rules of exponents that if you have addition in your exponent, you can break that up as two different powers being multiplied. And if you're like, wait, what? It's easier if you see it after I've done it. E to the kt times e to the c. Well, we're used to doing it from here to here. If you have two powers with the same base multiplied, you add the exponents. Think about it as x cubed times x to the 5th. Well, that's x to the 8th because you add the exponents. Let's get rid of that little example there. We don't need that. Okay. Now, this whole thing, e to the c, is just a constant. So we're just going to relabel it as a constant. And we often call it p or a. I'm going to call it p, e to the k, t. And we should recognize this as the standard equation for exponential growth or decay. And we know that this constant here, p, is your initial value. So this, right away, they tell me in the problem that we start with 120 grams of yeast. So y equals 120 e to the kt. And I could have just gotten to here right away by simply saying, oh, I know that this differential equation is the differential equation version of exponential growth and decay. It's actually the definition of exponential growth and decay, that the rate of change is proportional to the amount of output you have. So you could have just said, okay, I know it's this, and skipped all this separation. But good review, if nothing else. So now I know it's not linear, that's out, and it's one of these two. Either 120e to the 24t or 120e to the t over 5. Now, this 24 grams per day, let's read carefully, because sometimes we're going to say, ooh, 24, that's in the problem. 24, that's right there. But let's read carefully. At time t equals 0, the weight is 120, so that's this, yes, and is increasing at a rate of 24 grams per day. Well, what does that mean? That means that the rate of change dy dt, given that t equals 0, is 24. That's not saying that that's k. Now we do know that dy dt equals k times y. And if t is 0, then y is 120. And so dy dt is supposed to be 24 when y is 120. And if I solve that for k, I'm going to get k equals 1/5. So my answer is not that one, but that one. Common mistake there is to think that it's the 24. But 24 is dy dt, not k, because dy dt is k times y. Okay. Next one. All right, multi-part problem here. First part, write an equation of the tangent line. Hopefully we like that problem because we know how to do that. So point slope form, y minus y1 is equal to m times x minus x1. And we're told that we're writing this equation of the tangent line at the time t equals 0. And we're told in the problem that the temperature of the potato is 91 degrees at time t equals 0. So I know then that I have y minus 91 minus is equal to m times x minus 0. And to get my slope, I just need to plug in either 0 and or 91 into my derivative. And so we have here dh dt, which is my slope, is going to be negative 1/4, and I'm going to plug in h, not t, so 91. Sorry, my stylus is being all jacked up here. 91 minus 27. And if we work that out, you're going to get negative 16 for your slope there. So we have y minus 91 is equal to negative 16 times x. I don't need the x minus 0. And then use that tangent line to approximate the internal temperature at time t equals 3. So then it's just y equals negative 16 16 times 3 plus 91. And if you simplify that, I believe you'll get 43. So that's part A. Part B, something we haven't talked about in a while, but a nice FRQ review, asking us to use the second derivative to determine whether our answer in part A is an under or over estimate. And so we know if the second derivative is positive, the function will be concave up, and the tangent line will be underneath the curve. If the second derivative is negative, the function will be concave down, and the tangent line will be above the curve. So I'm just going to go ahead and clear all this tangent line out of here. I don't need that actual answer anymore. And let's look at the second derivative here. So I'm actually going to simplify the first derivative first before I think about the second derivative. It's going to be negative, I'm just going to distribute here, negative 1/4, seriously, h plus 27 over 4. Just a little cleaner to see how easy this second derivative is. It's just power rule. But I do have to remember second derivative. I need implicit differentiation here because it's h, not t, that I'm dealing with. So it's going to be negative 1/4 times dh dt. dh dt. And so then when I plug back in the dh dt there, because that's what I'm given, that's then negative 1/4 h minus 27. Well, the negative 1/4 times the negative 1/4 is going to give me positive 1/16. And then as long as h is more than 27, this thing will always be positive because it's positive 1/16 times a positive number. And they tell us that it is always greater than 27. So that means that we are concave. That means that my second derivative is positive, which means that my function is concave up, which means that my tangent line is underneath the curve and thus an underestimate. I'm not going to write that down because I'm struggling to write with my stylus right now, and you don't want to watch me struggle to write that down. Just rewind and listen to what I said. Clear that out. Part C asks us to actually solve. And like we talked about to start the last video, the only way I can actually solve is if I use separation of variables. And so if I bring everything with a g over to the dg side and everything without a g over to the dt side, I'm going to get, so hopefully we can write this time. Oops, maybe I can write if I choose the writing implement. I'm going to get the quantity g minus 27 to the negative 2/3 dg equals negative 1 dt. I chose to leave the negative on the other side. It doesn't matter. You're going to have to solve for g in the end anyway, so whichever way you do it is fine. All right. So now I take the antiderivative of both sides. I try to. Antiderivative, both sides. So I add 1 to the exponent and then bring that down. So that's going to be positive 1/3. And then divide by that gives me 3 g minus 27 to the 1/3 equals negative t plus c. I only need the plus c again on one side. Now I could go ahead and solve for g at this point, but because I need a particular solution that I'm then going to plug a number into, I want to actually find my c first. It's just a lot easier if I do that. So I'm going to plug in 91 for g and 0 for t. I'm going to leave the algebra out here and just let you do that. If you do that, you should get that c equals 12. And so now I have 3 times the quantity g minus 27 to the 1/3 equals negative t plus 12. If I go through a couple steps to solve that for g, I should get g equals the quantity negative 1/3 t plus 4 cubed plus 27. And then if you plug in 3, g of 3, because it wants us to use, or based on that model, what is the temperature at t equals 3? G of 3 is equal to 54 if you simplify that all out. And then part D, just a totally unrelated question, wants us to do another separable differential equation. So again, let me get rid of this, pause, rewind if you need it. Let me do this last little separable piece here. I separate, and I'm going to get 1 over y squared, or y to the negative second, I'll say. Y to the negative second dy is equal to 1 over x minus 1 dx. Take the antiderivative of both sides, add 1, divide by that, and I'm going to get negative 1 over y is equal to, this time I can't do the add 1, it's similar to the previous page, where this is going to be the natural log of the absolute value of x minus 1, x minus 1 plus c. And again, I have an initial condition here, so I'm going to do that first and say I've got negative 1/3 is equal to the natural log. If I plug in 2, I'm going to get the natural log of 1, which is 0. So that's just c. So then, let's scroll this up a bit here. I'm going to have negative 1 over y is equal to the natural log of the absolute value of x minus 1 minus 1/3. And then all I'm going to do is I'm going to say, well, if 1 over y is equal to that, then y should equal 1 over all that. Just kind of cross multiply here. And I'm going to leave the negative 1. I'm really just thinking multiply the y to the other side, then divide all that. So negative 1 over ln absolute value of x minus 1 minus 1/3 is equal to y. Sorry for the stylus drama. All right, longer video there, a lot to go over in those last two, so thanks for watching.